we go. The recording is on. Um, it's about time for our second exam. We're slightly behind schedule, but it's okay. I think we're going to be okay. So that means exam two is going to be next Wednesday. Okay. And the practice exam is here. I'm not going to talk about it today so that you guys have some time to kind of look it over, try it out, and try to see if you can answer the questions by yourselves before on Wednesday, and then we'll talk about it on Wednesday. Next Monday will be the last day before the actual exam for you guys to bring up some questions if you want to, and then we'll have the actual exam on next Wednesday. All right, so are we good so far with the scheduling of the exam? We good? All right. So with that said, we are just moving on to more examples of, using TTP to write code in C and C++. So what we'll do today is to look at, some recursive code. Um, have we looked at Fibonacci for this class? No? Okay. So we're going to start with something that's less complicated, and then we'll move our way up to more, complicated stuff. And once again, getting what is it? Um, River Spider to work is going to be really important. So if you have your own laptop computer, please, go ahead and try to install it on your own computer. On the other hand, if you're using the computers in the lab, you can also install River Spider on a thumb drive, and I think that's going to be very helpful, with all the programming assignments that you'll be starting to get soon. Okay. So if you come in a little bit late, go watch the earlier part of today's lecture about exam two. It is being recorded, so it's already recorded. All right, so we'll go ahead and take a look at some sample programs that we'll be kind of playing with today. And let me do this. This is going to documents, CISP 310, River Spider. That's where the script is residing. And then I can now edit a C program, okay, in the temp folder. We'll just call that Sigma. Okay, there we go. All right, so as usual, pound include standard integer.h, just so that I can use uint8 underscore t, and we'll call this, just function f. Okay, it's very, you know, the name doesn't really, it's not that useful, and it has one single parameter n, and we are going to return if n is greater than 0, or in this case, I can do something a lot easier. Okay, so this is going to be cryptic, and some people will frown at this. Okay, if return n question mark n plus f of n minus 1 colon 0. Okay, all right, so I think that's probably properly cryptic, and then we just have a local variable x in main called x. X gets f of we'll just say 3. 3 maybe, yeah, 3 is good. Then return to 0 at the end. All right. So do we have any questions about the source code itself in C++ or C? This is plain old C, but since it's a subset of C++, it's kind of the same thing. So do we have any questions about any line of this code? Okay. So no questions about number 4 or line 4, the ternary expression, particularly how n itself is used as the first item in the ternary expression. Exactly. Okay. So it's a very implicit thing. Okay. When an integer is used in the context of a Boolean in C or C++, it is basically saying if it is not 0, blah, blah, blah. Okay. All right, very good. So what we'll do is now we'll convert the program. Well, we'll test the program first. Okay. So what do you think is the value of x when we get to line 10? In other words, what is f of 3 going to return? So 3 is non-zero, so it's going to be 3 plus f of 2. 2 is non-zero, so 2 f of 2 is 2 plus f of 1. F of 1 is 1 plus 0. So that means the whole thing is going to be 3 plus 2 plus 1 plus 0, which is 6. Okay, so that's my speculation. Okay, 6 should be the result that is stored in local variable x of main by the time we get to line 10. That's the behavior in C. Okay, so this I'm not even dropping down to the assembly programming language level at this point. So are we good so far with that observation? Okay, so we'll try it. We'll give it a try first. So we'll go to the temp folder and then just go like gcc-d-o. We call that what? Sigma. And then sigma.c. Okay, run compile the first time, sigma, list the program, put a breakpoint on line 10, run the code, and then print local variable x, indeed a 6. Okay, very good. So now we're going to look at the assembly language implementation and see how this is done. All right, so anytime you guys have a question, please do not hesitate to ask, okay, because that is kind of important. And kind of the value of a class that is meeting in person too is you can ask questions anytime you want to. Okay, all right, so same trick, replace the beginning of each line with slash slash with a space. There we go. All right, the entry code is just no op, and then because we are now treating main as a function, so we'll do the proper thing and call main from the entry code, which has no name. So we basically have to push the return address. So we first calculate the return address to be 6 bytes away from the LDI instruction, decrement D, STDA, that's the actual pushing, and then we do a JMPI to main, and then when main returns to this point, it is just going to be a halt instruction. So these 6 lines of code we have been using, I think, since last week or so. So hopefully it does not cause any, doesn't have, you don't have any questions about that. But if you do, please ask. All right, so here's the entry code of main. And the way I usually write my code is I immediately put in the end of a function, which is LD, BD, increment D, and then JMPB. So just because I keep using these 3 instructions doesn't mean that you do not have to understand what these 3 instructions are doing. Okay, so the first one, pops the return at well, it doesn't pop. The lines 80, not 18 and 19 together is the pop. It pops the return address back into register B, and then JMPB is continuing execution wherever B is pointing to. Okay, so you still have to remember what those 3 lines are representing in terms of stack operations. Okay, so do not just try to memorize those 3 lines of code, because if I use anything other than these 3 lines of code in a different sequence, then you cannot recognize that anymore. It will jump back to line 6. That is correct. So as no, that's you mean the 6 on line 2? That 6 is referring to the number of bytes, not lines. Oh, okay. I might have misheard. So 6 bytes away from the LDI instruction is where we find the halt instruction, and that's why this is the return address. Yep. So this program, as it is, can run, and not very exciting. It just calls main returns right away. It goes back to halt. Now, because I have the tool to do this, really kind of efficiently, I can probably just go ahead and do it. So let me open up this and go to my River Spider folder and just run it. Okay, so I'm just going to run sigma.ttpasm, and then it should assemble. I don't see any problems with that, and apparently not. Okay, maybe I forgot to save it first, which is not going to be the first time, right? Yeah, I forgot to save it, just like what I said I would forget. Okay, fine, save. All right, try again. Yeah, these were the original comments. And why is it not doing it? Did I use the wrong file name? That's possible too. TTPASM, it is written. And okay, so let me check whether that's the right code. Yep, that is the right code. So why is it not doing that correctly? Hmm. Maybe it's not refreshed. I think that's a delay. Yeah. Okay. All right. So if you look at the analysis tab, this is the really basic shell of a program. The entry code calls main. Main returns to the entry code, get to the halt instruction. Done. Okay. So now we're going to go back and start to kind of put some more code into it. Actually, I do have it in a different tab, which is here. There we go. All right. So main has one local variable. So that means, it's the only variable is going to be at an offset of 0. LVS is going to be the offset to the last local variable plus the size of that particular variable. So that's our LVS here. So now we have to add the code to allocate and deallocate for the local variables. So that's typically just LDIB with and the LVS, local variable size, subtract that much from the stack pointer to allocate, and then when we need to exit, we have to add that many bytes back, or add the offset back to deallocate before we can get to the return address. So the sequence has to be this, okay? It has to be deallocating for the local variables so that the stack pointer points back to the return address. All right, so that is done. So now we can move on to this line here, okay? So now we have to implement F. So now we go to here. F is the entry point, and I'm just even going to copy and paste a little bit here, because the return code should look pretty much the same for everything, or they can be the same for everything. Okay, but if I want to be tricky in the final exam and use an entirely different sequence of instructions to do the return, you should be able to recognize it. Okay, so I'm just warning you ahead of time. Do not get fixated to the sequence of code that I use in class. Okay, because the actual sequence of code to get the same thing done may not be the same in the exam. Okay. Hmm? Yeah, just make sure that you fully understand everything, because when you fully understand everything, then you cannot be tricked by that sort of thing. All right, so in this case, we do not have local variables. So that means f underscore LVS can be just a 0. So if that is the case, then when we access our parameter, which is n, that is just f underscore LVS 1 plus. This one is for skipping over the return address. The return address is the last thing pushed by the caller, and therefore it is at the offset of 0 from where the stack pointer points to. So that makes the parameter at 1 byte off from where the stack pointer points to. So are we getting all this? Okay, why the labels are defined the way that they are? Okay, so well, let's go ahead and just kind of make this function do absolutely nothing and put a halt instruction here instead of actually returning. So we'll pretend that f is fully implemented and just finish the caller code over here. So over here, we're just going to say, okay, we'll just pretend that f is all done. So we have to push the 3 first because that's our argument. So we do LDI with 3, decrement D, LSTDA to push it on the stack. Then we have to push the return address on the stack, which is LDIA dot 6 plus, decrement D, STDA, and then we can now JMPI to the function that we are calling. When it comes back, we have to increment D to deallocate the argument that is still sitting on the stack, and then we can store the return value, which should be in register A, to local variable X. So we do LDI B because we cannot use register A. A is still containing the return value. So we do LDI B with main underscore X, which is the offset from where the stack pointer points to local variable X of main. Add BD, that to return register B to the address of local variable X. And all we need is a STBA that will store the return value from the function to local variable X. So now that we have kind of the shell of everything done, what we'll do is we're going to run this code as it is with the halt instruction in function f right at the entry point, because we want to identify what location is used for what, and we want to identify the individual frames of both functions. You go like, what two functions? What are the two functions here? Main and F. That is correct. So we have two frames by the time we get to the halt instruction. So just like usual, we are going to use a spreadsheet in the shared folder so that you guys can have access to the spreadsheet right away to look at the stack. So we're going to have a more or less a picture of the stack. The difficult part is I cannot give you an animation of how the stack changes. So you kind of have to make that happen if that is what you want to do. So today is 2025 1103. And just like before, we have location 255 at the highest location, 254. Okay, so we'll do the more systematic way like this. Okay, so we can just kind of drag this down a little bit. And then now we have the hexadecimal version, dec to hex of this thing. So we have both the hexadecimal and the base 10 representations. Okay, there we go. And then we'll try to describe, or to try to specify what is at those locations. So this one is the return address to the entry code, okay, which is the halt instruction. The address of the halt instruction should be here. That's the only thing. This is the only thing from the, oh, I shouldn't say the only thing, because main has a local variable x, right? So now we have, this is the return address. This is x of main. So these two, okay, is the frame of main. It only has these two items. It has the return address. It has no parameters, but it does have one local variable. So let me use color coding here, just so that it is easier to identify and go like, oh, okay, they kind of belong together. It is one logical unit. At this point of time, X is uninitialized. So technically speaking, we should put a question mark here to basically say, we have no idea what that content is. But because we know RAM is initialized with all zeros when we power up the simulator, so we kind of know that it has a content of 00, but it should not be assumed, generally speaking, in programs. And then we push a 3 on the stack. So that 3 is parameter n of function f. So that is a 3. We know that should be here. And then we also have a return address so that f can return to main. So we will have return address back to main. That would be that's also just a return address. So these 2 bytes over here, that is the frame of function f, okay, or one invocation of function f, because as we'll see, there will be 4 invocations of function f altogether. Okay, this is just the first one. So let's go ahead and pick a color. We'll try to pick the light red here. So, do we have any questions about this picture? About what location has what value? What is the meaning of that particular location? Do we have any questions about that? And where should the stack pointer be at the halt instruction inside F, which is right at the entry point? It should be pointing to FC. That is correct. Okay, so we are anticipating the stack pointer to be pointing here. All right. So are we good so far? So this is the kind of way that I would try to understand the material, is to write some code or take a program that is already done, stick a halt instruction somewhere, look at the stack, and be able to explain what is happening on the stack, looking at the trace itself. Okay, so now we are going to take a look, at the trace after we run the code. So we go back to here, make sure that I save the code. Yes, it is saved. And now we go back here and resubmit the code to the assembler. And this is why River Spider can be really useful because you can write a very small chunk of code and watch it happen and then be able to go back to the trace and go like, okay, let me see if I can explain every single line of what is happening. So let me just double check the source code is what we want it to be. We have the halt instruction here, so this is correct. So now we go to the analysis tab, okay? So if you want to do a quick thing to do, all you need to do is to focus on what we write on the stack. So we can now quickly identify that this is pushing the return address to the entry code, and then we change the stack pointer to FD because we just allocated for that 1 byte for local variable X. And then we overwrite location FD with a 03, which is our argument when we need to call F, and then we overwrite location FC with 19, which is the return address back to main. And you can go to the assemble tab and look at location 19 to double check and verify that as well. So when you look at location 19, it is indeed right after the JMPI instruction. That means it is the correct location to return to after the invocation of function f. So are we still doing okay so far? All right. Hmm? What is in function f? No, 19 is the return address from function f back to main. It is what is stored on the stack. That is correct. It is pushed on the stack. Okay. So when you look at these individual ones and then you compare to what we anticipate to be on the stack, let me get rid of the one from last week. There we go. That's exactly what we are seeing on the stack. Except we know this is location what 06, I think, and this is location 19. Okay. So are we doing okay so far? Because I'm just constructing the stack, as we speak, so that we can see, oh, okay, now we have the frames all set up correctly. Okay. So now we can proceed. Okay, we can now proceed to implement function f itself. So the first thing I would do if I were you, to implement a particular function is to say, let's forget what the function actually needs to do. I just want to return a random value of 42. Okay. The reason why I want to do this is to make sure that there's nothing wrong in main. Okay. So that I can trust, the shell of the code that I have here. And if you do something like this, you can even put in a comment here just for testing function f and main, okay, need to replace this with actual code. So this way I can remind myself I'm just testing the program at this point. It's not the actual finished product. Okay. So we'll go ahead and make sure it's saved. Okay. It is modified but not saved. Now it is saved. And then we can go back and run it again. So this is really important to be able to iteratively write the program step by step and be able to kind of double check along each step that it is all good up to this point. Okay, so this is all done. We go back to the trace, and what we should expect now is this location should be the hexadecimal version of 42. So that would be a 2A because 42 is 2 times 16. That makes 32 plus 10. 10 is A. So we're expecting location FE to be overwritten eventually to 2A in hexadecimal in the trace. So we go to the trace. And we just kind of double check things a little bit. We go like, oh, yep, that's exactly what is happening. And might as well check that we are ending at the halt instruction that we're supposed to. And when we do get there, the stack pointer is 00, which means the stack is fully balanced. Okay, so if I were you doing this with GitHub or any type of get or revision control, I would check it in. Okay, because I can now say the program is working as expected up to this point. even though f is not implemented. But the shell is working, okay? The returning is working, the local variable of main is working, the assignment inside main is working. So I got at least a certain portion of the program working up to this point. So I would check it in with a comment of, okay, now it is time to implement the actual content of function f. All right. So let's go back to the source code. Okay. And now, what we need to do is to implement this instruction, this statement here. So let me just kind of put it here and stash it over here because that's kind of where it belongs. So now I can comment out this line, okay, in case you want to keep it around but don't want to delete it, just comment it out. And now we can implement the actual, function here, um, which is a ternary expression. So with any type of ternary expression, the first thing you need to do is to evaluate the expression itself. So we'll go ahead and evaluate it, which also means we need to get to the value of parameter n. So you probably have recognized that this is the way to do it, which is LDI, the offset, blah, 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 and so on. So I'm going to show you a cheap way to do this as an alternative. All I'm going to do is to do a CPR CD, and I'll leave it up to you to comment what each line is doing or what is in the register that is being modified. So at this point in time, on line 15, once I execute this statement, register C would be the same as the stack pointer, which means it is now pointing to the return address of function f. But that's not the address of parameter n because parameter n is 1 byte after that. So I'm going to use an increment C to get to the address of parameter n. And now that we have the address of parameter n, I can do LDCC to get to the value of parameter n. And then once we have that, then we can quote unquote compare that to 0, which is in the form of NCC. Because if C was 0, then the Z flag would be set after the AND instruction. But you cannot do a JNZI. You cannot jump if it is not a 0. So the only thing you can do is a JZI. So I'm going to say, okay, this is going to go to the then portion of the ternary expression of the conditional statement. Otherwise, it would jump to the else portion of the ternary expression. So now, we just have to say, okay, where is the then portion? I will stick it here, and then it would do a unconditional branch to the end if of the conditional statement. So you can look at the ternary expression as a conditional statement with the else branch and the then branch, and also a point to indicate where the whole thing ends. So this is the shell of a conditional statement. If um, parameter n is non-zero, I should end up at the else. If n is 0, I should end up at the else 0 label. So let's just say that I cannot really track my own logic and I go like, I'm not sure this is working or not. What am I going to do? Test it with halt instructions. Okay. So I'm just going to stick a bunch of halt instructions here. Yes. CPR is not compare. Copy register. Yep. So that's the kind of question that you can try to answer yourself by looking at the opcode table. But that's exactly why I'm here, is to tell you to look up the opcode table. Think of me as a parameter that is passed by reference. I just pass the reference along. Yeah. So, but at this point, I want to debug my program. Okay. I want to see if I get to the correct label depending on the value of n. Okay. So the way it is right now is I am calling f with 3. Okay, because I'm pushing the 3 here. So I would even comment here. Okay. 3 is the parameter or argument to function f. Okay. so that I know, which line, I need to change later on. So save the code, save, there we go, and then run it. Okay. I forgot to comment the two halt instructions, which is what I should do. I should probably just do it and then come back and trace it again. Give me a second. The reason why it is good to comment the halt instruction is the analyzer or the trace would actually display the entire line. So it would be good to kind of comment this and go like, okay, and up here, if and only if n is not 0. And then I'll also comment the other one that says and up here, if and only if n does equal to 0. Okay, so that makes the trace a little bit easier to read. So I'm going to rerun the trace here. But this is why, River Spider is handy, because without this tool, you can watch my video all day long, but it's not the same as making your own example to see if you understand the concept. Okay, so I just need to go up here and go like, okay, we end up here if and only if n is 0. It's not working because I did pass 3 as a parameter, so I'm so glad it's not working, or something is inconsistent with what I think it should be doing. Okay. And why do you think I'm so excited? Because now I have a problem to solve. And I'm not sure whether I'm common, in terms of the people who choose a career in computer science. Um, but I think most people who choose to be a software developer or programmer or even a software engineer really can use that kind of mentality. It makes your day pass like there's nothing. You go to work, at the end of the day, it's like, did I work today? Because it felt like that I just went to Six Flags. Your own version of Six Flags is like, oh, I went to a lot of interesting rides, but that didn't feel like work. It just felt like fun all the time. And I get a paycheck for this. Cool. That literally was what it felt like at work for 8 years when I was in industry until they promoted me to management. That was their mistake, man. That was their one single mistake. If they did not promote me, I would still be working as a software engineer happily. But once they promoted me to to management, it's like, I can't do this. I can't do this, man. All right. Okay. The program is not working. Great. Okay. So the C flag is a 0. That is correct. Okay, a 3 should not have done that. So JZI did not happen, and it went to the else case. So, and that's how we end up here. So the JZI should have gone to the else case, and then the other case should not be, should just kind of fall through. So I just found my bug. Okay, it was just my logic being wrong. So let's go back and change the program. So, from the perspective of you just learning, you should check in the program that's wrong and then fix it, and then check in the program that is correct. And then do a visual diff or difference to take a look at the two programs so that you know, oh, okay, so that's a problem and it is fixed this way. So, I'm going to do it kind of the clumsy way. Okay, so I'm going to save this program, with a different name. Okay, we'll call it um, Sigma 1.ttpasm. Okay, and then switch back to the original when I make the change, when I fix it. So the JCI, which is when n is 0, should go to the else case, not the then case. The then case is just going to be fall through. Okay, that was my problem. So save it. And now I'm going to show you, a tool that I use a lot. Okay, just to look at the difference between the code. What did I change and how is it different from the old one? Vim can do this. Okay, you can do a div dash D, so you can supply two files and it would display the differences between those two. So I would provide your sigma dot ttpasm. It's going to complain because if I try to open the file twice, it's going to go like, this is not good. It's okay, if it's okay as long as I don't change it. So ttpasm again. Yep, see, this is what it's trying to complain about. That's okay. So that shows you the difference. On the left-hand side is the original code. On the right-hand side is the corrected code. So in the original code, I go to the then case if and only if the Z flag is a 1, that is not correct, okay? Because when n is 0, I want to go to the else case, okay, to be consistent with the C code. So that's the change. Blue line means it is the same. No, not blue line means it's changed. The line is not exactly the same. It is changed. Green is inserted, and then if it's red on one side, it means that line is deleted. So it's color coded. Is that okay? So this is one way to do it. There are many other programs that can visually display the differences between programs or between source text files. I encourage you to find one that works best for you, because not only for this class, okay, but also for your other programming classes, there will be, I recommend you to keep versions of your code so that you can kind of do the diff to see what you have changed. Okay. All right, so I have no use of that window anymore. The code should have been changed. So I'm going to run it again. Okay. It is important that after you make a change to fix something that you thought was wrong, that you run the code again to make sure that code is now correct. All right. And I don't know why there's a synchronization issue. It is a synchronization issue for sure, because I think I saved this code. Yep, it is saved. Alrighty. Oh, I made the change to the wrong file. Darn. Okay. Good catch. JZI here to else. There we go. All right. Thank you. Do it one more time. But if you use get git as a command, then you don't have to save it under different file name and run into the problem with that I just ran into. There we go. All right. This is good. Okay. So just because I can get here because n is not 0 does not mean that when n is 0, I will get to the right label. So I'm going to check that too. So I have to go back here and then change that argument from 3 back to 0 to make sure that this time it ends up, at the right place as well. So change this back to 3. And depending on your editor, I definitely program mine so that to do is highlighted. So it's easy to spot. Oh, okay, exactly. Reminder to myself. Okay, need to change this. There we go. Save and then run again. So this time it should get to the other halt instruction. So you might think, wow, this is going to be lengthy. Writing a program like this is going to take a long time. Well, trust me, if you don't do it this way, it'll be longer and much more frustrating too. There we go. So we're good. Okay. So go back to the code. Go back to here. Okay. And now we go like, okay, now that we know that part is working, we can now kind of get rid of this. This reminder is no longer useful. Okay. Huh? Yeah. So we can now comment out the halt instruction. Just in case we need it back. All right. So which one is the easy one to do? Oh, looks like this one is easy. We just have to specify a value of 0 to return. Just put that in register A. We're all done. Okay. This will take 2 bytes. Okay. LDI A0 will take 2 bytes. The LDIA part is one single opcode, and then we have an immediate operand, which is going to take a second byte. Okay, so I'm going to go like, I want to save one byte of instruction and use this instruction instead. What does that do? It subtracts register A from register A and then store the result back into register A. What? I don't know what register A has, but whatever it has, it becomes a zero. Huh? Register A is just 8 bits. That's all it is, okay? It's just eight zeros and ones. It is not even a part of the stack. Register A is not in memory at all. It is in its own little register bank thing, you know. Yep. All right. So pretty sure that's gonna work. So now we can kind of focus on, okay, the then portion then. Okay, the then portion says we kind of need to call f again with n minus one. Well, guess what? Register C has the value of n at this point. So now we just need to decrement it by one and then push it on the stack. Okay. And yes, I intentionally did not write any comments because I think if you try to follow this code and try to figure out this, how it works, it will sink in a lot better than me commenting the code and you're just reading it. Okay? But remember to spend the time to do it because if you don't spend the time to do it, things will not sink in, it's not going to gel, and then by the time you get to the final exam, you would notice. I would just kind of put it that way. You would notice. All right. So this is me pushing n minus one on the stack, and then we need the return address. Okay, but that becomes easy to do. Decrement D, stda, that pushes the return address on the stack. Call function f, increment D to deallocate the argument that is sitting on the stack. So now the result of f of n minus one is now in register A. Yes, 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 but I did. Which one? Which line? Line 24. Oh, you're correct. It is register C. Yep. Thank you. Otherwise, the program would not work, and then I'll be very excited because now I have something to fix again. All right, cool. Thank you. That is correct. All right. So now we increment D. Okay, so f of n minus 1 is now in register A. I just have to add it to n, right? So if people are saying, "Oh, that's easy to do, just do this," okay, that would not be good. Why is this not good? Because Tech, you said the register C had the value of n. Oh, maybe it's because of the decrement D, so we just have to increment D first. Increment C, sorry. That would also not work. It has to do with one little thing in the caller callee agreement. Let's go back and check that contract. See, this is the kind of stuff that you should do when you buy a house. Make sure you understand the contract when you sign a loan. It's like, yeah, read the contract carefully. Okay, so we want to understand from the callee side and the caller side what is the contract. What about the registers? Okay, so it is here. The value of registers A, B, and C are not assumed to be preserved after a function call. But you just called yourself. Surely you know yourself, right? No, because calling any function that is calling yourself is included. Recursive call is not immune from this particular rule. Registers A, B, and C are not assumed to be preserved. So that means at this point, when we come back from the function, at this point, we don't know, what register C has. Okay, we cannot assume that it is still n minus one. So that means, okay, we don't have a choice. We actually now have to recompute n as a value. Okay, so I can still do the same trick: CPR, CD, increment C, and then do LD, CC. So now n is back to register Z, add AC. That should do it. Okay, so hopefully I have another bug somewhere in here and you guys cannot catch it yet. Okay, so we'll just quickly run this program. Now, when you run your program, when you test something like this that is recursive, don't go for a lot of recursion. Okay, go for the simple recursion. Okay, f of 0 is not going to do the recursion, but f of 1 is going to have one level of recursion. So do that one. So we're going to change this to a 1, and then make a to do. Okay, just testing, change back to 3 after testing. There we go. So just a little note to myself. And now we want to look at the stack and go like, okay, what is going to happen this time on the stack? So what is going to happen is this is going to be a 1, and it's going to call itself again. When it call itself again, this becomes a 0, which is n of f again. And then this is going to be a return address to function f from function f. Okay, so those are the two things that should be sitting on the stack. And I'm going to highlight this with a yet another color. Let's pick something that's greenish. There we go. So now we have three invocations of the stack. By the time it's supposed to return a 0, and then we are now expecting 1 plus 0 to be stored back into this location here. So we want to check it. Okay, we want to see if that is actually going to happen. So now we switch back to the tool and then just kind of run it on the command line. Oh, make sure I save it first. Yep, I did. Good. There we go. So I'm keeping my fingers crossed that the program does not work. Because debugging really is the most important part of programming. Okay, the amount of time that you spend with programming and the amount of time that you spend with debugging is not even close. I think there's something wrong already because it's taking so much time to re-upload the trace data. So we're going to take a look. Okay, so hopefully I think I'm getting my wish. Oh yeah, look at this. It is supposed to be a lot shorter than this. Okay, so what do you do when you see something like this? You just track it down. Okay, you just really track it down. And typically I use the stack push as a clear sign of how to track it down. So this is the return address, and this is pushing the 1 on the stack, pushing the return address to um, back to main. And we'll double check everything too. Okay, don't leave any stone unturned. So we go to, what was the location? 2F. So we go to location 2F and say, okay, it really is the correct address to return to in main. So we're good there. And then we see, okay, what do we push next? We should be pushing a 0 next. And we did put a 0 next on the stack. And according to the picture of the stack, the 0 going to location FB is indeed correct. So everything seems to be correct up to this point. Oops, sorry. Go back to the trace again. Okay. And then we see, what do we do next? Ah, it is now going for another call when it is not supposed to. Oh, wait, it is. Okay, this is the return address. And so in the function here, we have the return address. Okay, so now we have to double check it is pushing the correct return address. Because if you specify the wrong return address, it will just return to wherever 17 is. If it's the wrong place to return to, then we have a problem. So now we go back to the Assemble tab, go to location 17, and make sure that it really is the correct place to return to from the recursive call. So 17 is right here, and it is indeed right after the JMPF. That is the right point to return to. So now we go back to this thing here and go like, okay, we got this location accounted for. And then we go back to the Analysis tab, And then we go like, okay, what else do we do? Ooh, look at this. Okay, it looks like it is going back, and then it just kind of repeat a whole bunch of stuff. It's calling again, rewriting location FB and so on. So we know the problem is happening uh, somewhere after this point. Okay, well, that's fine. So we then go here. N is 0, and CC is checking whether it really is 0. It is really 0. It should go to the else case, and it jump a bunch of lines, subtract AA, turn register A to 0, and then at that point it should return. Okay, so now we look at the code that is doing the return. We pop the return address 17, and then we increment register D. It gets back to FB, and then we continue execution to the increment D, which is for deallocating the argument that is still sitting on the stack. The stack pointer get back to FC, and then we do a CPRCD to get to the stack pointer. Aha, wrong instruction, because we are supposed to increment C and not increment D. Okay, we should not mess around with the stack pointer unless we are pushing, popping, or trying to. We should not change it. Okay, when you try to access something, you can read it, but you should not change it. So I just found my bug because that increment D should have been increment C. Hmm? Yes, except for push and pop operations. So when you're pushing something, then you have to decrement. When you're uh, when you're popping something, you have to increment, or when you're allocating and deallocating. Okay, so I just found my bug. So so this is the sort of thing that I like to do. I did not actually inject a bug into the program intentionally, but it is. It even tells me which line. This is nice. I like myself. Cool. That's my bug. Okay, it is all saved. Let's try that again. Hmm? So it increments. So we copy register D, which is the stack pointer, to register C. It points to the return address. But when we increment it by 1, then it should point back to the parameter, because the parameter is one location or 1 byte higher than the return address. Yep. So the moment that simulation finished submitting the trace code, the moment that it took so long, I knew something was off. So now we go back here, okay, increment C, the code is all fixed, and it should terminate with location FE being a 0. So we are good. All right. So if f of 1 is returning, everything looks good. We get back to the right halt instruction. Register D, the stack point is balanced. So that means I can probably get back to f of 3 to see that it will put a 6 into local variable x of main. All right, so we're going to go back and check it. Okay, so we go back to the to do. Okay, change that back to a 3, get rid of the comment, save the program, and run it again. This time we should expect a 6, but the trace will get longer too because um, we will have multiple frames on the stack. So, and when it's doing this, oh, too fast. Okay, so this time, we are going to expect this is to be a 3, this to be a 2, and then this would actually repeat several times. So it would go from 3 to 2, 2 to 1, and then down to a 0. And then, so at some point, the stack pointer will be going as low as 246 or F6 as a value. Okay, so this is my speculation. Okay, so this is the sort of thing that I do is even though I was pretty sure the program is working, I still want to see it. I still want to double check and verify that the stack pointer only went as low as F6, but never below that. Okay, because I don't want anything that is unexpected. But before we do that, we're gonna change up the colors a little bit because each color is representing a particular frame. So we'll pick some of the other wonderful colors that we are offered, like so. So now we have so at the lowest point or the deepest portion of the recursion, we have one, two, three, four frames of F existing on the stack at the same time. Okay, so we'll double check then. Okay, we'll go back to the trace, got a few things to do. The first thing is to make sure a 6 is stored back into X, okay, not surprising. But we also want to see how how the stack pointer has been changed. So we focus on the stack pointer and try to find out how low it got. Now there are a few ways to do this. Um, you can do a search, okay? So you can go to, I think it's Control G to search, but you can always go to Edit and then go to Find and Replace. You're not going to replace anything, okay? You're just trying to find. So you can now start with D equals to something, search in specific range, and this range is just your column D, and you can specify column D kind of like this, okay? That's the entire column, and then just find. So here so it's a quick and easy way to locate specific things. So FF, FE, FD, FC, FB, FA, F9, 8, 7, 6, back to 7. So we know that the lowest it got was F6, which was kind of what we expected. Are we good so far? All right. So now we get rid of this window and the program is done. So do we have any questions about this? Yep, sure. Mm-hmm. Hmm? The okay, so this needs to go back to the code. So the part that adds them together is here. So line 33 is what is adding them together, but only one level at a time. Because line 33 is implementing the actual C code of this add here. Because at that time, when we get to here, register A has the return value of f of n minus 1. Register C has the value of n, so you're basically adding n to the return value of the recursive call. So this is another reason why commenting this is really important. Because when you get to line 33, what are you going to write as its comment? That will trigger you. That will hopefully it will prompt you to ask, okay, I kind of know what is in register C, but what was in register A? Why are we adding to register A? Because register A has the return value from the recursive call of f of n minus 2. So so you have to kind of comment all of this, with respect to this document here. This document is the caller callee agreement. So you have to read this, okay? And as you go through the code, you basically say, okay, what do I know about this register at this point? Why does it have this value? You have to do all the explanation. So let me do one thing first. Okay, so I'm gonna zip up, the two code here, the two program. One is in C and one is in TTP ASM, and we'll put it into sigma.zib. Sigma.zib. There we go. And then over here, I'm gonna send you guys another announcement with both the C and the TTP ASM code. If you're already signed into um, Google Drive, you can actually make a snapshot right now because this is the finished form of the assembly version of the program. So it would be kind of handy to have it available. Unless you already have River Spider up and running, then you can just make your own. So that makes it kind of easy too. So Sigma sample program, C attached, and then we attach it. Sigma.zip. There we go. And it is still recording. Okay, so we do have the full recording of today's lecture. Um, and this is important, okay? To go back to this program, go to the TTP ASM version and comment basically every line, okay? And say, okay, what is this line doing? How does it relate to back to the C code? The key is how does it relate back to the C code? The key is not to say, oh, add AC means we're adding register C to register A. I know that already. Okay. So what you need to do is to say, okay, but what exactly is in register C? How does that relate to the C code? Oh, register C has the value of parameter n. What about register A? What does register A has what does it have when we get to that line? Oh, register A is the return value of the recursive call. So that is the sort of thing that is important. It's relating the assembly code, what is in each register, to the C concepts, to the C program. All right. Are we okay with this? Okay. All right. Okay. So now I'm going to tell you one thing. Now you can interpret it any way you want to. Um, in certain classes, the professor does not let people use their phone. I'm not going to do that because I don't get distracted by you guys using your cell phone. But if you want to distract yourself in the class using your cell phone, that also is not my problem. So that's up to you. If you're using your cell phone to take notes, that's that's good too. Okay, so I have no idea what you're using your cell phone for, and I just want to tell you, what some other professors do in their class. They do not let people use their cell phone in the class, but I do recognize that some people actually take notes using their cell phone. I have big thumbs, okay, so I can't take notes on my phone, but I do have a nice keyboard. Alrighty. So do we have any questions about calling and returning and stuff like that with functions? Because if there are no questions, we're going to move on to talk about structures, which is even more fun. So are we ready to move on to structures? You look a little hesitant. Yeah, go ahead, please. Hmm? Are we rewriting? I do not believe so in this case, except for one location. So when we go back to this trace here, it is a one-way street from here to here, and then just a one-way street back to. So unlike Fibonacci, where it has double recursion, the location is not reused for something else. The only location that was allocated and then got changed is this location here. Yeah, so we are changing X because we have the store, right? Because in main, the return value of f is used to change local variable x of main, which is at this location, 254. Yep, yep. So that means this table here, you can make a copy too. So I think this is also important. Okay, the difficult the difficulty of this table is it is static. Okay, it only shows you at a certain point what the stack looks like, but it is not dynamic. In other words, I cannot show you as the program executes in the trace what the stack looks like because that requires a dump of the stack content every single time we access or every single time we change the stack pointer. Okay, so that is something that makes it a little bit harder to track, but you can still um, deduce what is on the stack by the stack related operations. So when you see how the stack pointer is changed, or when things are written on the stack, or when you're accessing things from the stack using the LD instruction, that's when you know that you're either storing something or retrieving something from the stack, and it becomes an important thing for you to understand is what am I retrieving or what am I storing on the stack? All right. So so did I address your question? Okay, very good. Any other questions related to the stuff that we have already talked about? No questions? Okay, very cool. So that means, we are almost ready for the first actual programming assignment where I give you the C code and you have to implement in assembly. So we're almost ready, but I'm not going to give it to you today. Hmm, Probably on Wednesday. Okay, so on Wednesday we'll talk about the exam from last semester, but at the same time, I'll give you a take-home homework so that you can actually do it. Okay. All right. So at this point, we're going to move on to the concept of structures, or just struct in C or C++. So we'll first take a look at a simple struct, example program where we define a okay. First thing first, pound include std int.h. Then I define the structure. So I'll define the structure. We'll just call the structure X here. But since I don't like, uh, X as a company, I'm gonna call this Y. Okay, there we go. So we're gonna have like a few members. Okay, so the first member is called A. The second member is called B. And the third member is called C. It doesn't really matter. I mean, for this program, it doesn't really matter. Int main struct y. We have a local variable called v1. Okay, and then we say v1 dot b equals to 78, and that's all we want to do. Okay, so look at this code. First of all, do we understand what this program is doing? Okay, I'm not making any copy. There are no copies here. I'm making an object. Very good. So Y, uppercase Y, is the name of a structure definition. I'm using the structure definition to make a local variable v1 that has that particular structure. Okay. So one way to look at this and to kind of remember, this is pretty easy, is to look at line 3 to line 7, which is the definition of the structure itself, as a cookie cutter. Okay. And then you look at line 10 and go like, I want to choose this cookie cutter called Y, and then go to your cookie dough and go like clunk. Okay. That piece of cookie is called V1. So V1 is an actual cookie that you use the cookie cutter Y to cut out. Is that okay? So what we do on line 11 is not to the cookie cutter, but to the cookie cut from the cookie cutter Y and go like, this little piece of cookie dough over here that we call B, let's reshape it a little bit to something. That is what we're doing. All right. But there are a few things that I want to illustrate just with a simple program like this. Okay, so we'll go take a look, just kind of slowly. Okay, we look at this in the GDB. We put a breakpoint on, say, line 11. Okay, that should be more than enough. Run the program. So now we're on line 11. So the first thing we want to do is to take a look at what is the size of the structure? What is the size of V1? What do you think it's going to be? Yep. Okay, it is 3. It's not really surprising, right? So I will go ahead and take a look at the address of V1, the entire structure. It is blah blah DD7D. Okay, are we good so far? And where do you think we can find member A of the structure of V1? It is the first member of the structure. The whole structure starts at location blah 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 DD717D. So where do you think we can find the first member of the structure? The same place. Why do you want to add one? What are you going to use that one byte for? Exactly. Yep. Yep. All right. So are we getting this point? Okay. Okay. So the first member of a structure is at exactly the beginning of the entire structure. But does it make sense to you? I think yes. Yes. What about the second one? What about B? Where do you think we can find B as a member? The next location, right? So increment by one, so that would be DD7E. Yep, not surprising. Okay, what about C? Just one more after that. Okay, so this is illustrating the structure and how it is stored in memory. Are we good so far? All right. Um, Not entirely. So in the case of the x86, the 64 AMD 64 instruction set, and how Linux and also Windows NT, is using the instruction set, every process, which is every instance of running a program, has its own memory space. So every single program has this location in the logical sense from the perspective of the program. But these are logical addresses, so the computer has a lookup table, so all the virtual memory space of each process get remapped to the actual physical space. So in actual memory, they're all over the place, but in terms of within the same program, they all have the same location, quote unquote, the same location. So to prove that, okay, to prove that, I will leave this program up and running. I open a new tab, and we're going to run exactly the same program, which is not a problem. Yeah, so I'm going to run exactly the same program, put a breakpoint on exactly the same place, run it to that point, and ask, where is V1? The same place. Every process has its own logical but virtual memory space, so they do not overlap in what there's no overlap of memory space, actual memory space between the processes. They're all protected from each other. It's like a multiverse. Every process is living in its own little reality bubble, just like us. Mhm. All right. So with with 6 minutes left, I'm going to give you the assembly version of this code that we're going to go over next Monday. Okay, again, but I'll do it kind of, hmm? This Wednesday I'm going to talk about the exam, the practice exam. This is not going to be in the exam. The exam will cover everything. Did we have double last time? I don't think we have double. We don't have floating point, so it's going to have floating point. It's going to have one question about the PDNC thing, the tracking down the circuit, what the gates are doing, and it's going to have one question about the processor architecture that requires you to really know, the pathways inside the processor, how multiplexers work, how registers work, how demultiplexers work, and so on. So, when you take a look at the exam that I have just put into the announcement, you'll see it. So none of this is actually in the scope of exam two. All right, so we're gonna do a quick. Now that we have 5 minutes left, I think we still got enough time. All right. All right. So the first question is, how is a structure represented? So a structure is represented by a bunch of labels. So y underscore a is defined to be a 0 because the label is defining an offset again. But this is the offset of where to find a member of a structure from the beginning of the structure itself. So that means YB is going to be a 1, but I'm not going to say a 1. I'm going to say it is where we find A and then the size of A added to it. So everything is relative. So YC is going to be YB 1 plus, and then Y underscore size is going to be the size of a struct y. So that's just going to be the offset to find the last member plus the size of the last member. So that's the size of y. So now we put in the usual entry code, no op, LDIA dot 6 plus, decrement D, ST, D. This is not really object oriented. It's just, encapsulation using structure because I'm not defining functions inside the class. So we are not going to deal with classes here. So that halt. So here's main, and then we're going to have the usual return code, LDBD, increment D, JMPB. So that's basically, just template code. Now, the most important part is where do we find V1 as a local variable on the stack from the perspective of main once we allocate everything? It's still zero because we only have one single local variable of V1 here, so it is naturally at the bottom of its frame. So it is still at zero. So this is not the mysterious part. The question is how many bytes should we allocate local variable size, LVS? So now the question is how many bytes do we actually need? Then you guys will go like, oh, 3. No, exactly. We want to use Y size. In fact, we want to say the offset to the last local variable from where the stack pointer points to plus the size of Y. So that is how we define the local variable size. And now with this, we can now do the allocation. Okay, so we just do the allocation the same way as before, which is LDI B with main LVS, subtract that much from the stack pointer for the allocation, and then add it back for the deallocation. So this part has not changed. So now when we look at this instruction here of where do we store the 78? Okay, so the 78 is the easy one, stash it into register A. So now the question is, where do we find member B of the structure that we know as V1? This is how we do it. So we load main underscore v1, which is the offset to the beginning of the structure. And then we specify y underscore b plus, because that is the offset to member b from the beginning of the structure. So this becomes the offset from the beginning of the frame to member b of v1 as a struct y. And then the rest is the same. Okay, add register D to register B, so it becomes the address of member B of the structure V1. And then once we have that, we just need to store that over here, and that's done. So from the perspective of the stack, what does it look like? So from the perspective of the stack, I'm going to copy certain parts of this, but not the entire thing. So I think I can copy this much. Okay, so we can now, this is all going to be gone. Okay. So in terms of what each location is used for, this is just return address. This would be these 3 bytes would be local variable x of main, but they are different members. This is member C of V1. This is member B of V1. This is member A of V1. So, so these 3 locations, they are all used for V1. The one that we should be changing would be 253 or location FD. So according to the code here, it's supposed to be a 78. So 78 is, I'm trying to do the conversion in my head. It is 64 plus 14, or 80 minus 2. So 50 minus 2 is a 4e. So this is supposed to be a 4e in hexadecimal. So we'll go ahead and check whether this program does what it's supposed to, and that should conclude today's lecture. All right, so save it and do a pop-d. Oh, okay, I did not do it like that. Okay, we can do it this way. Submit. struct.ttpasm. Oh, it doesn't want because I have I am excited, except I'm out of time. No, it doesn't complain. There's no mistake here. Did I specify the wrong? No. Okay, I think it's still working. Nope, it's definitely not working. All right, do it one more time. Sometimes it takes two takes. Don't know why. I think it is async. Something is asynchronous. It's doing it, but when the code thing is done, it's not. There we go. So now we're doing good. And location FD is supposed to get a 4E value. FD to get a value 4E. That's exactly what is happening. All right. So this is the kind of like the first lecture or the beginning of something like this. So at some point we're gonna have double pointers to a pointer that points to a pointer that points to a structure, and we're supposed to change one of the members of the structure that turns out to be a pointer itself, and so on and so forth. We're going to make linked list in this class, topics that are in CISP 440. And when people say, but that's not fair, I have not taken CISP 400, that's okay, because I'm not asking you to write the code. I will give you the C code. You just have to translate the C code to assembly code. So the focus is entirely different compared to CISP 400. All right, so for today's lab. So today's lab is down here. I got everything configured already. It is call frame. Okay, so this is today's lab. And the access code is framed. I have not unhide it yet, so give me a second to publish. There we go. So you should have access to it. So I'm gonna write down the access code. It is framed. This one is a whole bunch of multiple choice tests, questions, so it should be pretty quick to get through. But try to read slowly because part of the class instruction is actually embedded into the lab itself. And once again, you can use the assembler. You can also use Logisim. You can use River Spider when you try to do the labs. All right. So I'm going to stop the recorder, upload the lecture, and